All right, welcome back. This lecture is going to be on one-tailed and two-tailed hypothesis tests. So this is a continuation of the logic of hypothesis testing with just a little bit of addition to it, which is the difference between directional versus non-directional hypotheses and then the associated one-tail versus two-tail hypothesis tests. So before getting into the new content, I want to go over another example of null hypothesis significance testing, just so that's fresh in our mind how that works. And so I'm going to review one of the examples that the textbook authors gave. So let's just say we're researchers and we want to test if money leads to more happiness. We randomly select a single person from the population and give this person $20 million. Sounds pretty good. I wish it was me. I'll point out this is, of course, a very artificial example. When we do research, we typically don't do research on just a single person. There is research studies that are case studies, but we would not do null hypothesis significance testing based on a sample of one. But this is just to show how it works. All right. So we've got our research study that has a sample of one, just this single person, and we all wish it was us. We get $20 million. Now, let's just say we also know that for all people, we've measured a bunch of people, and there's a happiness scale where we have people rate that they're not at all happy with a score of 0, and they can give any number from 0 to 100, with the end point being 100 extremely happy. And so when you give people this rating scale, hey, on a scale from 0 to 100, how happy are you? The average happiness is 70 with a standard deviation of 10. Notice the symbols for the population parameters. We've got mu, which is the population mean, and then we've got sigma, which is the population standard deviation. So what we're saying is we know that in the population of people that we're interested in, and this could be like all people in the world, this could be all US residents, something like that. But the population of interest, we happen to know the population parameters. Okay, often we don't, but again, we're just using very simplified examples, and in this case, we know the population parameters. So what we want to know is, if this is what is typical, if this is what to expect on average, is giving somebody $20 million going to make this person more happy than average? Well, our person gets a score of an 80. So let's try to make a statistical judgment about this score. We want to know whether the results support our hypothesis that money leads to more happiness. That's the research question. Does money lead to more happiness? Okay, so what we want to say is, okay, well, on average, people report a 70. Our person gets an 80. Does this score seem different enough for us to conclude that money leads to happiness? And kind of more specifically, would this score of 80 be so different or such an extreme deviation from average for us to say, no, this person can't be sampled from this, we'll say, normal population. They must be sampled or taken from some other population of very happy people that have all this money. All right? So that's kind of the way that we're setting this up with null hypothesis significance testing. So hypothesis testing proceeds through 5 different steps. And for the purposes of this class, it's really important that you're able to work your way through the mechanics of all 5 steps, which is why I'm giving this additional example in this lecture as well. So the first step of null hypothesis significance testing is to restate the research question as a null hypothesis as well as a research hypothesis about populations. We're interested in making inferences about people in general, so we're going to do a study that involves a sample, but ultimately we're making predictions about what happens in general among populations. Okay, so our research hypothesis is that money leads to happiness. People with a lot of money are more happy compared to everyone else. In symbols, we're going to state this as H sub A. Recall that the research hypothesis is also called the alternative hypothesis. It's the alternative to the null, and that's why we use the subscript H, the subscript A. So H sub A is the way that that's described in formal notation. What we're saying symbolically with our symbols here is that the population mean for people that have money is greater than the population mean for everyone else. So what we're saying is that on average, money leads to happiness. People with a lot of money are more happy. Recall that that's the direction of the inequality symbol here. Higher numbers, higher happiness score, more happy compared to everyone else. So we're saying on average they should report a greater amount of happiness than everyone else. The null hypothesis is simply the opposite of the research hypothesis. So if the research hypothesis is that money leads to happiness, the null hypothesis is that money does not lead to happiness. So to explain it further, people with a lot of money are either equally happy or even less happy compared to everyone else. So if money doesn't lead to happiness, they're equally happy or even less happy. Have to take into account both of those possibilities. And the way that we symbolize that with our notation is H sub 0, sometimes called H sub naught, but just be able to recognize your two symbols. And then what we're saying here is that on average, people that have money are either less happy or equally happy compared to everyone else. Okay, so on average, when they're given that 0 to 100, we expect that their number is going to be lower than everyone else. Okay, so we're basically taking into account all possibilities. Our research hypothesis is we're predicting the effect that money is going to have. Money should make people more happy, and therefore they report a higher number on the 1 to 100 scale. Now we're just using a very simple study where we've got a sample of one person. But we're saying that in general, if you give anybody money, okay, generally people that have money, in general, on average, they should be happier than everyone else. And we're going to test this hypothesis with a single person, a study of one. All right. Now the second step is to determine the characteristics of our comparison distribution. The comparison distribution is just the population situation if the null hypothesis is true. Well, if the null hypothesis is not true, if money does not lead to happiness, then the population of people with money should be just the same as people without money. So if we know the characteristics of the population of people without money, that tells us exactly the situation if the null hypothesis is true, because then people with money are exactly the same as everybody else. So our comparison distribution is just what everybody else looks like. Okay, so if the null hypothesis is true and if money has no effect, people with money look just like everybody else. So if we know what everybody else looks like, we've got our comparison distribution. So again, this is something we kind of have to imagine. This is a phenomenon that has been studied. Perhaps this 0 to 100 metric is used quite a bit. There's all kinds of data on people, and so that we know on average, the average happiness score is 70 with a standard deviation of 10. And so this kind of lets us know what happiness scores are typical and what happiness scores are less typical. So we can see that among people in general, which we're saying would also be the case if money has no effect, it's very typical to get a score somewhere in the range of 65 to 75, with the most typical score being a 70. It would be less typical, that is more rare, to, to, to sample somebody that has a very high happiness score. It would also be less typical, that is more rare, to kind of randomly sample somebody that has a very, very low happiness score. So happiness is normally distributed. The advantage of being able to assume that happiness is normally distributed is we know the probability of obtaining a happiness score when converted to a z-score. Okay? We know the probability of scoring higher than or lower than any particular z-score. And that's important for establishing our critical value that is associated with our levels of statistical significance. So this third step is to determine what is the cutoff score or the critical value that we need on the comparison distribution at which we're going to reject the null hypothesis. So by convention, statistical significance levels in psychology and other social behavioral sciences are associated with 5%. 1% is another conventional level, but I'm sticking with 5% for now. So what this means in terms of statistical significance is we're saying we're looking for a sample result that would be unlikely if our sample comes from a population that is just like the untreated population. So what we're looking for is a sample result that is our actual person who got the money and then reported their happiness. We're looking for a result of that little research study that would be unlikely among people that don't get the money. Well, we know among people that don't necessarily have money, the average happiness is 70, and we know then that the top 5% of that distribution is associated with a z-score of 1.64. So when we convert our happiness scores to z-scores, we know that if you get a z-score on happiness that is more than 1.64, that's kind of rare. Like there's only the top 5% of people that would get a happiness score that when converted to a z-score would be more than 1.64. So that tells us what to expect ahead of time in our comparison distribution. That is people that don't have money. So what we're going to say is, well, okay, among the person that we gave the money to, if their score would land in this critical region, we're going to say, that's not typical. That's not typical of normal folks. Hence, it must be the case that money had an effect, because it's just not typical to get a happiness score that is this high. And it just so happened we got a happiness score that was this high among the people, among the person that we gave the money to. Hence, that result seems much more supportive of the idea that money leads to happiness, and I would reject this null hypothesis that money didn't have this effect of making people happy. So it is a very challenging logic, but that's the way it works. Whenever you hear statistical significance, whenever you hear hypothesis testing, this is the setup. This is the logic. All right. So our critical value establishes this region of significance. If we get a sample result that falls in this region of the comparison distribution, we will reject the null hypothesis and we will find support for our research hypothesis. So that's what we're doing at this third step. The fourth step is we actually would go out, we collect the data. We already know that our person got an 80, but we set it all up ahead of time. We run the study, we collect the data, and then we see what our sample's score is. And then once we get that score, we convert that score to a z-score so we can locate that score in this normal distribution. Okay, so at this stage, we know that the person got the raw score of 80. We want to convert it to a z-score so we can place it and see if that 80 does in fact fall in our region of significance. Okay. So we are going to calculate the z-score by using the population parameters of 70 and 10. We calculate a z-score here in the same way that we learned in previous modules, where we take the individual score, the x-score, subtract the mean, and then divide by the standard deviation. That will give us a z-score of 1. And kind of makes sense. If we look at it, we say, well, if a standard deviation is 10, this person is 10 happiness units away from the mean. They're 1 standard deviation away from the mean. So now what we need to do is we need to locate that score in the distribution, and we need to decide whether to reject or fail to reject the null hypothesis. So what we're going to do is we're going to compare the actual z-score that we calculated with our sample to the critical value. And we're going to say, is this z-score that we calculated, is it more or is it less? If it's more, it falls in our critical region. If it's less, it does not. Okay? So we're comparing this 1 to the score that we needed, which was more than 1.64. So our result ends up being we're going to fail to reject the null hypothesis because our result is within the bounds of what we would expect by chance if the null hypothesis is true. Okay, in other words, it didn't land in the critical region. The score is actually a score of 80 that is associated with a z-score of 1 would actually be considered typical among people that don't have money. And so for that reason, we're going to fail to reject the null hypothesis. Recall that the null hypothesis was that people that have money report the same happiness or even less happiness than people that don't. So we can't reject that idea. What we're showing is that the result of our sample was that this person is reporting, we would say an amount of happiness that would typically be found in this comparison distribution of regular, normal people that don't get all the money. All right. Now, importantly, we don't prove the null hypothesis to be true. We only show that the result failed to support our research hypothesis, okay, because we were not able to reject the null hypothesis. So there's a little bit of nuance to it, and as I do more lectures and as we get to some of the upcoming topics, we'll get into this more, but we don't prove or support a null hypothesis. We just fail to reject it, right? We say that our study was inconclusive. So that's a little bit of nuance, but I'll get into that in subsequent lectures. Now, as the textbook authors went over, you might be interested to know that psychologists have done these types of research studies, and this little example has been based on previous psychological research. So what this, even among lottery winners, so psychologists have studied lottery winners basically as examples of what happens if something really, really positive happens to you. Does that affect your happiness? And the results are similar as what you get in this fictional example. People that win the lottery are not much happier 6 months later than people that don't win the lottery. They also looked at people that have bad things happen to them. So they looked at people who unfortunately became paraplegics through a random accident. Turns out you would think that, oh my gosh, if you become a paraplegic, your life is ruined, you're going to be miserable. It turns out among that group of people, they're not any less happy than other people 6 months after the accident. So the very interesting thing, and this has been replicated, is that if some major life event happens, it doesn't necessarily have a lasting effect on happiness. Um, if it does, it's not going to have a big effect. Um, so we have this kind of amazing ability to return back to whatever our set point was. Um, so and we're bad judges of that. So people often think that events, whether it's a positive event or a negative event, is going to have a lot stronger impact on their happiness than it ultimately does. So in some ways that's good. We're very resilient to negative, um, but then unfortunately that we're also kind of not as affected as we would like to be by the positive as well. And then when it comes to money, interestingly, some research shows that um, really past a certain amount, more money doesn't make a difference, at least on people's report of positive emotions. So the positive emotions that you feel on a day-to-day basis, um, it matters up to a point. So I think up in the number was something like $75,000. Leave it to the economists to figure this out. But then after $75,000, people that have more than $75,000 don't necessarily report more positive emotions um, in their life. They do report generally having a better life, so there is that, but it doesn't result in positivity. Anyway, tangent, but um, when it's possible to bring in some interesting psychological research, I figure why not. All right, let's get back to stats though. Um, and particularly the topic of this lecture, which has to do with directional versus non-directional tests. So in null hypothesis significance testing, we calculate a statistic, and here are several examples of statistics that you're going to learn this semester. We're learning the Z statistic and the Z test, but there are several others. But when we calculate that statistic, we evaluate the probability of getting that statistic if the null hypothesis is true and there is no effect. Typically, we have a directional hypothesis. So here would be two examples. We would have a hypothesis that a treated population will have a higher score on average than an untreated population. So that was the example that we did last time, that we would say that a group of students that gets memory training should have a higher exam score than people that don't. But another example of a directional hypothesis would be predicting a reduction in something. So for instance, you could have a hypothesis that a treated population that gets medicine would have less than or fewer symptoms than a group of people, a population, that doesn't get the medicine. But either way, we're specifying some direction, either an increase or a decrease, an improvement or a reduction. That's a directional hypothesis. We're predicting a direction of an effect. There are other times, however, that we have a non-directional hypothesis, which would be symbolized as the mean for the treated population is different than, as in not equal, to the untreated population. So we might say, for example, that we think that giving a group of students memory training will result in having a different exam score than students that don't get the memory training. Different like how? Well, there's a chance memory training could work and it could improve exam scores. However, there's also the possibility that by giving students this extra thing to do, it actually distracts them from learning the concepts for the exam, in which case exam scores might actually be worse, right? So it's kind of like this unestablished procedure, and we're saying to ourselves, maybe it will work, or maybe it will not work and things will get even worse. So that would be an example of a non-directional hypothesis where we're just predicting that there will be a difference between these two populations, a treated versus an untreated population, but we can't be confident about what the direction of the effect will actually be. All right, just to elaborate this a little bit further. So directional hypotheses are associated with one-tailed hypothesis tests. So a directional hypothesis predicts a particular direction or a particular difference between two populations. So for example, students who have memory training will score higher on the exam. Another example would be that people who take medicine will have fewer symptoms than people that don't. Okay, on average, kind of just in parentheses in your mind, like mental parentheses, I want you to just insert on average. I try to include it, sometimes I don't. So when we have a directional hypothesis, we're going to use a one-tail hypothesis test. So this is a testing procedure where we've got the critical region on the comparison distribution only on one side, okay? So when we predict that the direction of the effect is going to be an increase, we place our region of significance in this tail, okay? So we've got this single region of significance only in one tail of the distribution. When we've got a hypothesis that we should see a reduction, like a reduction in symptoms, we're going to place our critical region in the opposite tail of the distribution because we're predicting a reduction or a decrease from average. Therefore, it only makes sense to look for a sample result that is in the lower tail of the distribution. Okay? An increase is associated with the upper tail of the distribution. A decrease is associated with the lower tail of the distribution. But in either test, it's only a single tail of the distribution, a one-tailed test. Okay? A one-tailed test will always be associated with a critical value of 1.64. Okay? Either positive 1.64 in the case of predicting an increase, or a negative 1.64 in the case of predicting a reduction. That 1.64 is the z that is associated with the upper 5% of the distribution or the lower 5% of the distribution. Okay, so 1.64 is the only number that you need to know for a one-tailed test. Our z, our critical z, will always be either positive 1.64 or negative 1.64, just depending on whether we're predicting an increase or a decrease. Okay. Now there's one other set of z's that you need to know that's associated with this 0.05 level of significance. But just as a recap, a non-directional hypothesis or hypotheses do not predict a direction of the effect. So for example, we might predict students who have memory training will score differently on the exam than people who do not have memory training on average. People who take medicine will have a different number of symptoms than people who do not take the medicine on average. Okay, so here we're going to do a two-tail test because the critical region of the comparison distribution is found on two sides or in the two tails of the distribution. So in this case, because we're accounting for both possibilities, that memory training could result in an increase or a decrease, we're interested in both tails of the distribution. Similarly, if we're not making a specific prediction about the effect of the medicine and we're taking into account, oh, there could be all these side effects and maybe there's actually more symptoms, or there could be less, we're interested in both tails of the distribution, and so we'll do a two-tailed test. What that means is when we do the study, we collect the data, and we calculate a z-score, we will consider as statistically significant a result that falls in either critical region. We could have a result that shows an increase that falls in the critical region in the upper tail, and if so, we will have a statistically significant result. We will reject the null hypothesis and find support for our research hypothesis. That would also be the case if we get a sample result that is much lower than average, that falls in the critical region, because when converted to a z-score, we get a z that is even lower than negative 1.96. Okay, so we've got these two different regions of significance. All right. So you'll notice that the non-directional two-tailed tests use a more extreme critical value of either plus or minus 1.96. We're still only interested in results that happen less than 5% of the time if the null is true. That is our threshold for statistical significance, otherwise known as the 0.05 significance level. Okay? Sample results that happen less than 5% of the time if we assume that the null is true and whatever we're doing has no effect. So what we see is that a z-score of negative 1.96 and positive 1.96 cuts the distribution and is associated with the lower 2.5% of scores and the upper 2.5% of scores. Okay. Because we're considering both tails of the distribution, we have to split that total 5% into the top 2% and the bottom 2.5% and the bottom 2.5% of scores. Together, that sums up to 0.05, so that's associated with our 5% significance level. When we only do a one-tail test, and in this case we've got a one tail in the upper tail of the distribution, we're putting that whole 5% in a single tail. What that means is that we can move our critical value back, and we've got a critical value that is only 1.64. So we have a less extreme critical value when we do a one-tailed test. We have a more extreme, and by extreme we just mean farther away from the center, farther away from the mean. So we have a more extreme critical value when we do a two-tail test. All right, so another important aspect of doing one-tail tests. If a one-tail test is used and the result is in the direction that is actually opposite from the predicted direction, no matter how extreme that result is, it cannot be considered significant. Let's return to our example of memory training and exam performance from the previous lecture. I've come back to it a couple times in this lecture, but we did the worked out example in the previous lecture. Let's just imagine that our training completely backfired and the student who completed our training actually scored much worse on the exam than average. Recall that average was an 80, and we get a student, our single student in our sample, that gets a 66. Well, let's convert that 66 to a z-score so that we can place it in the distribution. Okay, these were the characteristics of our comparison distribution. These are just students that don't go through the memory training. This is what we know happens over kind of the long run. Let's convert 66 to a z-score. We'll just plug in our numbers. 66 minus 80 divided by 7. That gives us a z-score of -2. Okay, the sign, of course, is very important. That negative tells us that 66 deviates in the negative direction, which makes sense because it's less than 80. So therefore, we've got a negative z-score. So let's place that in our comparison distribution. Now let's go back to the original setup. In our original setup as a one-tailed test, we had predicted that memory training would work in that it would result in an improvement on the exam. So we had set up our test to have a z-critical of 1.64, which was associated with the upper tail, this top 5% of the distribution. Okay, we had predicted that on average, training would result in a higher exam score than the no memory training group. Null hypothesis is that we would get a result that would be an exam score that would be less than or equal to the no training group. So in this case, we would fail to reject the null hypothesis. Notice that this result of getting a 66 is entirely consistent with our training, this sample being sampled from our trained population of being less than or equal to our no training group. So in this case, we're going to fail to reject the null. What we're saying is that we do not have evidence that the memory training improved exam performance. It's often the case that researchers generally prefer to use a two-tailed test, except where it's very clear that only one direction of the outcome would be of interest. So in this particular case, if it would be of interest to interpret this effect and say, well, yeah, but it backfired, and so we have a statistically significant result showing that the memory training actually significantly reduces exam scores. You're not allowed to do that. And let me explain why. I'll explain why in just a little bit. First of all, when do we use a one-tailed versus a two-tailed test? It has to do with when we have a directional versus a non-directional hypothesis. We use a one-tailed test when we're very confident in the direction of the effect and we are not interested in interpreting a result in the opposite direction. So for example, our research hypothesis might be that memory training improves exam performance. On average, training results in greater exam scores than no memory training. Null hypothesis, memory training does not improve. Okay. In this case, we'll use a critical value of z as positive 1.64 and only consider results that are above this cutoff. Here's another example. We're very confident that the medicine reduces the number of symptoms. In symbols, the average number of symptoms for people that take medicine is less than the average number of symptoms for people that don't take medicine. Null hypothesis, medicine does not improve symptoms, so that taking the medicine actually results in a greater than or equal to amount of symptoms. In this case, we're going to use a critical value of negative 1.64 and only consider results that are below this cutoff because we're looking for a reduction from average, lower than the mean, less than the mean, okay? And it needs to be less than the mean by enough, okay, by a significant amount, such that when converted to a z-score, we get a z that is even less or even lower, okay, more extreme in that direction than negative 1.64. Okay, now we use a two-tail when we're not confident in the direction of the effect. So we could just say that memory training has an effect on exam performance. We're not sure, it could really help, it could really hurt. Well, let's try it out. What do we have to lose? Okay, in which case the null is just that the memory training does nothing, has no effect. Okay, notice our symbols, we're saying that here on average, students that get the memory training are not equal to, different than people that don't get the memory training. Different how? We're not specifying, just different. Versus the null hypothesis is that they are equal. In this case, we'll use critical values of plus and minus at the same time. You have to use both at the same time. Plus and minus 1.96. And we'll consider results that are either above or below these cutoffs. So we could get an exam score that is so positive that when converted to a z-score, it is higher than 1.96, in which case we'll say, yeah, memory training has an effect. It helps exam performance. Alternatively, we could get an exam score that is so low that when converted to a z, it is even lower, as an even less than 1.96, in which case we would still interpret the effect. And we'd say, well, I have to reject the null hypothesis. It seems clear that memory training does have an effect. What is the effect? Makes exam performance worse. Okay? So if we aren't confident, we think it could go either way, we do a non-directional hypothesis and a two-tailed test, but we have to adjust our critical value. Okay. This one is a little bit tricky to understand, but we would do a two-tail when we have an idea about the direction of the effect, but we would still interpret a result in the opposite direction. So let's just say we've got our directional hypothesis, and we predict that training improves exam performance. But we're saying, yeah, but if it backfires, I'm still going to interpret it, and I know that. Like I'm pretty sure, I'm pretty confident, but if I'm wrong, I'll still want to report a statistically significant reduction in exam scores, or it got worse, in which case I'll still use the critical value that are associated with that two-tailed test. And here's why. Interpreting results that are the opposite of what was expected when we only have that one-tailed test changes the definition of statistical significance. So in the case where we set up our one-tailed test and we got the backfire result, if we interpret this result as a statistically significant result, we've just changed our definition of statistical significance. In this case, we end up going from statistical significance is less than 5% to statistical significance is less than 7.5%. Because we would have interpreted any result that fell in this critical region, and we're now interpreting the result that falls in this critical region. So we now have 5% plus 2% equals 7.5%. We need to limit ourselves to a strict definition of statistical significance as being sample results that happen less than 5% of the time, assuming that the null is true. It is against the rules, illegal, whatever you want to call it, to to set ourselves up doing a one-tailed test and to interpret a result on the other side, because now we're saying that statistical significance are sample results that happen less than 7.5% of the time, assuming that the null is true. We've just made that standard less impressive, less difficult. And in subsequent lectures, I'll go over the kind of the danger in doing that. All right. Just to wrap a couple things up, it turns out that null hypothesis significance testing is somewhat controversial, and there's actually researchers that say you should not do it at all if you believe that, even though it is the standard way that most research is done, including psychological research, including medical research, including pharmaceutical research. There are many researchers that say, I wish we could just be done with this. In fact, even the American Psychological Association, many years ago, convened a committee, got a task force together. They came out with recommendations that said, we should really kind of abandon this null hypothesis significance testing. And very few people paid attention. So why would people be against null hypothesis significance testing. One complaint is that researchers often misinterpret a non-significant result as meaning that the null is true, that there really is no effect. Okay? So that you do the study, you get a non-significant result, as in we didn't get a sample score that was extreme enough to reject the null. And so what then the misinterpretation then is that the null is actually true, that memory training doesn't actually work, or that the medicine does not actually reduce symptoms. This interpretation is not actually proper. Failing to reject the null hypothesis does not make the null hypothesis true. Failing to reject the null hypothesis could be due to several things, most often that the study didn't have enough power to detect an effect that really does exist. Let's take our really bad study with a sample of 1. It could be the case that we put this single randomly selected student through our memory training, and this person honestly is just one of those folks that can't be helped. Let's just say the memory training is good, it's effective for most people, but not just our randomly selected person that we just happen to get. Okay, so our memory training looks like it doesn't work, but it turns out it just really didn't work for this unique person. If we had had 5 people, 10 people, 20 people, 100 people, what we would see is that our memory training might be differentially effective for all of these different people, but on average, like thinking about a typical result, it does work and it does improve exam performance. Okay? So that's a good reason to say just because you do a study and you don't reject the null, we don't necessarily want to conclude that the null is true and our memory training doesn't work. We could have just had a bad study, and we might not have had enough statistical power to detect an effect when it really does. Statistical power is underlined. That is a concept that I will elaborate also in future lectures, but I just want to introduce this concept, which is to say, just because you reject the null, you should not be in the position of saying, oh, well, the null must be true then. No, it just means that based on the result of your study, you don't have sufficient evidence at the time to reject the null and support your research hypothesis. Okay, great. So glad I got that bullet. I'll talk about the concept of statistical power in future lectures. If you're reading any research for any of your other classes, you might see the results of statistical tests written up in these research articles. So there's kind of a convention for reporting results, which is that you say the statistic that you used, you say the statistical test that you performed, you give a test value. So I don't know why I didn't include Z, but that's what we've been working with. Instead of all these statistics that you haven't learned yet, okay, we can say that we did a Z. That test was associated with a particular value, like our actual test value, the actual Z-score that we calculated, and that Z-score or some other test statistic was associated with a level of significance. So we set up our test, we determined a critical value, and we would get a test statistic that was more extreme, as in larger than, and it was large enough to say that we have a statistically significant finding at a probability of less than 5%, or a probability of less than 1%, or a probability of less than 0.001, which is even less than 1%. It's 0.1%. So basically, when you see a p less than one of these conventional levels, what the researcher is telling you is that they have a statistically significant result, that the results of their data are unlikely if the null is true, that the results of their study would be unlikely if their procedure had no effect, or their intervention had no effect, or their treatment had no effect. So they're saying because our sample results are unlikely if the null is true, what we actually did had an effect. Okay. Alternatively, if what they write is same thing, here was our test result, comma ns, they're saying the result was not significant. That is, there was not sufficient evidence to reject the null hypothesis. Whatever result they were looking for, there was not enough of an improvement, or there was not enough of a reduction, or there was not enough of a difference between a treated group and an untreated group to fail to reject the null. In which case, they'll just write comma ns. This was a non-significant result. Back to the drawing board. We'll have to improve our study and try it again. Oftentimes, what you will see reported is something called an exact p-value. For instance, p equals 0.039. What an author of a paper might be trying to convey is the exact probability that a result, a sample result, this big or bigger, would occur, assuming that the null is true. So they're saying if we assume that the null is true, the probability of our data are 0.039. Notice that this 0.039 is less than our conventional level of 0.05. So rather than writing probability less than 0.05, which means statistically significant, they're just kind of being more precise, which is to say the probability is, I can tell you how much less it was less than 0.05. It was 0.039. What you need to do as a reader is say, is this probability less than the conventional 0.05? If yes, we have a statistically significant result. Finally, people might report a p-value that is close but not quite statistically significant. For instance, p equals 0.055. It didn't quite make that threshold of being less than 0.05, in which case you might see an explanation that the result approached statistical significance or that the results were marginally significant. What the author is trying to convey is that we got close, but we didn't make it. Okay, we didn't make that commonly agreed upon threshold of 0.05. Okay, so that was a recap of the core logic as well as the steps of null hypothesis significance testing, as well as an explanation of the difference between directional and non-directional hypotheses and conducting a one versus a two-tailed test. I hope that you know under which circumstances you use one versus the other, and also know which critical values are associated with both. Okay, that's it for this lecture. Thanks very much for watching.